So in this video, we're going to talk about time value of money. I will not have done my job in this course or in this video if you walk away not having a firm foundation, an intuition for what time value of money means. Did you know that often when someone wins the lottery, let's say they win a huge jackpot, $100 million, that's the advertised jackpot, $100 million, they'll often have a choice. Let's say the jackpot again is $100 million. They'll often have a choice, either receive $50 million in one payment today, done, receive $50 million, or receive the $100 million paid out as $5 million a year for 20 years. Okay? Often lottery winners have a choice. The headline number paid out over time versus like half of the headline number just given to you today. Why would that be? Why would someone, in fact, take the smaller number that's immediate versus the much larger number paid out over time? Well, the answer is the title in this topic, time value of money. Money is worth different amounts at different points in time. Specifically, as we're going to learn, money is worth more now, all else equal, than that same amount of money in the future. Okay? If you don't leave this video with that intuition, again, I am not doing my job. All right. So in most financial decisions, we have costs and benefits that are spread out over time, and we can't directly compare them. Our fundamental key intuition is that a dollar next year is not the same as having a dollar today. And this is an example of time value of money. So time value of money is the difference in value between money today and money in the future. Specifically, all else equal, money today is worth more than money in the future. So if a friend came up to you and said, all right, which would you rather have, $100 today or $100 a year from now? The correct answer is $100 today. And that's not like a preference, like, I like pineapple flavor and you like cherry flavor. It's not a preference, it's an objective fact. $100 today is worth more than $100 a year from now. Why? Now, some of you, I can tell, probably already answering in your head. The answer is because it can earn interest. I could take the $100 today, go put it in a bank, and it will grow to be worth more than $100 a year from now. Okay? So for example, if you put $100 in the local bank at a 6% interest rate, how much would you have in 1 year? How would we calculate it? I know some of you are already figuring it out in your head, but let's calculate and let's write down a formula for answering this question. So I'm going to switch over to Excel. And I'd recommend if you have these slides open and want to follow along and do the calculations with me. I think finance is a lot about learning by doing. So if you're doing this while I'm doing it, I think it's quite helpful. So I'm going to do these calculations. I encourage you to do the calculations with me. Okay, so let's take a look. We have an interest rate of 6%. We have $100 today, and the question asks, how much money would we have 1 year from now? If I took that $100, I took this $100 and invested it at 6%, how much money would I have 1 year from now, right? That's what I'm interested in. All right. So let's do it. So what would we have in our bank account? We would have the original $100, but then we would get 6% of that $100, which is $6 a year from now. So we'd have the original $100 plus 100 times the 6%. Right? Now that's going to be $106. If I hit enter, you'd see the 106. But what I'm going to do, rather than leaving it this way, notice in my equation, the B3 term right, is in the first and the second term, so I can pull it out. So instead of writing this as B3 plus B3 times B1, or 100 plus 100 times 6%, I can write it as the original $100 times 1 plus the interest rate, right? So 100 times 1 plus R. And that's my 106 right here. Okay. Now, I'm sure many of you did that in your head. You didn't need Excel to do it, but it's important to give the first exposure to this fundamental formula that we're going to be using, which relates present values, the money I have today, to future values. Okay. All right, let's toggle back to our slides. And let's take a look at the second question. So this is like the first question, but in reverse. It's a flip. If your friend offers to lend you $100 today in exchange for $104 in 1 year, how much would you need to deposit in the bank account today in order to have enough to pay her back in 1 year? So we're going to get $100 from our friend today. I want to know how much of that 100 do you need to take and put in the bank account so we're sure to have 104 to pay her back in 1 year. All right, let's go back to Excel. So what do I have? The amount I owe the friend in 1 year, that's 104. And the question is, how much do I need to invest today so that I have $104 1 year from now? So you can see intuitively, this is the exact reverse or flip of the problem that we just did. And so if the last problem, the answer was, oh, well, it's the amount I invest times 1 plus R, right? This answer is going to be that amount in the future, the amount I need, divided by 1 plus R, right? How much do I need today so that it grows, aka it's multiplied by 1 plus R, to be that amount in the future, is just taking that amount in the future and dividing it by 1 plus R. So that's exactly what I'm going to do. I'm going to take the $104, that's the amount that I need in the future, and I'm going to divide it by 1 plus the interest rate. Close parentheses, hit enter, and my answer is $98.11. So if my friend gives me $100 today, and I know I owe her $104 a year from now, I immediately can take $98.11 from it, go put it in that bank account, which earns 6%, and it will be, I can set it and forget it, just like in an infomercial. Put it in the bank, that $98.11 will be $104 a year from now. Good. Let's go back to our slides. All right. So what about problems that involve more than 1 year? So this is the general equation. The future value at some time n equals the present value times 1 plus r to the n. So remember, in that last example, we had $100 that we put in the bank account today, and we grew it for n equals 1 year, right? So the PV was 100, and we multiplied it by 1 plus r, remember the r was 6%, to the power of 1. Well, what if we invested that amount for 2 years, or 3 years, or 4 years, 10 years? What would change is that power of n. The n would be 2 years, or 3 years, or 4 years, or 10 years. Okay? This is our general equation for single cash flows. It's going to be a really important equation in the course, top 10 for sure. So get to know it and understand it. So again, let me just go through the parts with you. So we have on the left-hand side the FV, right? FV is the future value, hence the F and the V. On the right-hand side, we have the PV. PV we call the present value. That's why it's PV. Right? R, right here, is the annual rate of interest. Remember in our last example, that was 6%. And N is the number of years. Okay? So those are the four components of this key equation. All right. All right, so recall that last example where we were investing money at a 6% interest rate. Suppose you place that $100 in a savings account that earns 6% compounded annually. Compounded is just a fancy way of saying that interest accrues annually. So if I put the $100 in today, in 1 year, and the interest rate is 6%, in 1 year, the bank is going to dump 6% of interest in my account, right? It will compound in that moment, okay? Well, let's think about moments afterwards. So after that first period is shown in this table below. So let's go through it. So let's actually just start at the beginning. So at today, which we'll call time zero, right? Time zero, we have $100 sitting in the account, right? That's the present value. Okay. In 1 year here, right, we will have $106 in the account. We already knew this given the calculation we made earlier. How did we get that? It's our original $100, right? This, right, times 1.06 right here, right? All right, but here's where it gets interesting. Here's where it gets interesting. In 2 years, let's jump to year 2 here, we're not going to have $112 in the account. So think about that. After 1 year, when we had our first compounding event, $6 was dumped into the account. But after 2 years, there wasn't just another $6 dumped in the account, so the account would have $112. That didn't happen. A little bit more than $6 was dumped into the account. Specifically, $6.36 was dumped in. So now the account has $112.36. Now, we could have gotten that number just simply from the equation, right? We know the equation. It was on the previous slide, right? It's just PV times 1 plus R to the second power. But ask yourself, how come I have more than 112 at year 2? And hopefully the answer that you're coming up with is, well, it's because I earn interest on that first year of interest. I earn interest on interest. Remember, I got $6 worth of interest that first year, right? So not only do I earn interest on my original principal, the 100 I put in the account, I also earn interest on the $6 of interest I generated that first year. That's why I have more than $112 in year 2. Okay. And on we go. Here you can see year 3. Here's year 3. We have $119.10. Year 4, we have $126.25. Year 6, we have $141.85. If you ever want to know how much is in the account at any point in time, you just apply the formula. For example, in year 6, right, it's just PV times 1.06 to the 6th power. What is PV? Remember, it's our original amount we put in the account, which is $100. Okay. Fast forward to 100 years, we will have $33,930.20. Now, that number is quite large. Why is it so large? It's because that formula we introduced has FV equals PV times 1 plus R to the N. The FV there represents exponential growth. In the finance context, this is what people sometimes refer to as the miracle of compound interest. So what I just showed you on the last slide is achievable. Imagine that your great-grandparents had invested that $100 in the bank at 6% interest 100 years ago. Right? What would their investment look like over time? That's on the next slide. It's the green line right here. Right? This is exponential growth here. So the $100, right, which started at time 0, finishes at more than $33,000 100 years later. Okay. Now, for exponential growth, you should know that the interest rate R really matters. Okay. This final number, when n is large, when there are lots of years, is very sensitive to the R. So you can see when the interest rate is 4%, we're talking about a final number after 100 years, which is around $5,000. If we take the R down to 2%, now we're talking about a number which looks less than $1,000. All right, let's look at this to gain some additional insights in the Excel sheet. So I'm going to flip over to Excel. So here I'm on slide 7. So here you can see the setup of your great-grandparents investing $100 at a 6% interest rate. Okay? And what I want you to do, again, if you're following along, and again, I encourage you to follow along in the spreadsheet with me, do it with me, is highlight these 3 cells, and then at the bottom right, this small green square, double click so that they fill down. Okay. And what are you seeing? Well, in column B, starting in row 4, I'm listing for you the amount in the account at various points in time. We've seen these amounts before, right? At time 0, there's $100 in the account. At time 1, there's 106. At time 2, we know there's 112.36, so on and so forth. But what we're doing in columns C and D is we're decomposing that amount in the account. Okay? So this 112.36 is made up of what? Well, certainly the original investment of $100, of course. $12 of interest on that original investment of 100. Do you agree? Right? 6% interest, right, on the original 100 would be $6 in the first year, $6 in the second year. That would be $12. Okay, that's the 12. Okay, and then the final column D here is the part that we mentioned earlier, which is super interesting, which is the interest on interest. Right. This 36 cents, remember, in year 2 is the additional amount we got from the interest in the first period, right? The interest on this interest in the first period. Okay, what I want to underscore for you is the following. In year 2, of this 112.36, interest on interest is pretty meaningless. The majority of the action, the majority of what explains the total amount in the account of 112.36 is the interest of 12 and the original investment of 100, right? That's $112 out of 112.36. But scroll down, right? Scroll down and see how this changes over time. Let's actually scroll down to the very end, year 100. Remember, we know how much is in the account 100 years from our initial investment, or from your great-grandparents' initial investment. It's $33,930.21, right? That's how much is sitting in the account. Well, remember, how can we decompose that $33,930.21? Well, 100 of it is the original investment. 600 of it is that 6% we got on that original $100 each year for 100 years. That's why it's 600. But all of the action, $33,230 of our $33,930 is the interest on interest, right? So when n is large, almost all the action is in this last bucket, the interest on interest. Okay. All right, let's flip back to our slides. All right, so remember our general equation that we laid out a few minutes ago, which relates FV to PV. It's given here. FV sub n, the future value at time n, equals the present value times 1 plus r to the n. So often it's useful to rearrange this not as a formula defining FV, but as a formula defining PV. And we can do that with some simple algebra. Let me just show you. Right? If we take this original equation, and we multiply both sides by 1 over 1 plus r to the n. So multiply both sides by 1 over 1 plus r to the n, right? Okay. These will cancel, right? And what will you get? You'll get PV equals FV sub n times 1 over 1 plus r to the n. So hopefully it makes sense to everybody algebraically how we can go from the top line here to the bottom line here. Okay? It's just a simple algebraic reorganizing of the original equation. Okay. Now, when we write the equation in terms of PV, the one below, we can think about PV as the amount of money that will make you just as happy or wealthy today as FV at some date, say n years in the future. That's how to think about PV. Okay? When we go back and forth between PV, present value, and future value, when we start with PV and go to FV, we often refer to that as compounding. We take some amount, some original amount we put in an account today, and we compound it to be some amount in the future. When we go the other way around, when we start with an FV in the future and bring it back to today, we often call that discounting. So suppose I have, $10,000 5 years in the future. If I want to figure out its present value, all right, the amount which would make me just as happy had I been given that amount today, we take that $10,000 and we say we discount it back to today. That we refer to as discounting. So just good terminology, compounding versus discounting to be familiar with, and you'll see me use it throughout the course. All right, let's do some time value of money problems. So the first one, what is the present value, PV, of $1,000 to be received 10 years from now, discounted at an annually compounded rate of 9%. Okay, let's jump back to our Excel sheet. We are on slide 9, that is the third tab. And let me just remind you, I'll write the equation here. Let me just remind you about the PV-FV relationship. So PV equals FV times 1 over 1 plus r to the n. So remember that from the preceding slides. Okay, so I've written out in Excel the components to the problem. So we have money received in the future, $1,000, 10 years from now, at a 9% interest rate. All right, so what is the present value? Well, according to the formula that we just wrote down, right, it's going to be the future value, right, that's the $1,000, times 1 over 1 plus r, that's the interest rate, to the nth power. So what is the present value of $1,000 to be received 10 years from now if the interest rate, or sometimes we call it the discount rate, because remember, we're going from a future value to a present value, that's discounting, so we often refer to this as a discount rate of 9%, the answer 422.41. Good? Jump back to our slides. Let's do another problem. A major new customer has just pushed back the start of its contract with your company by a full year. The contract called for an upfront payment of $10 million at the start of the contract. So you were expected to receive $10 million today, right? Start of the contract, but it's being pushed back a year. Now you're going to receive it a year from now. If the interest rate is 5%, what is the cost to your company of the delay in receiving the upfront payment? Okay. So again, let's jump back into Excel. Okay. So remember, you were going to receive $10 million today. Now that's being pushed back 1 year, right? So that $10 million is now coming 1 year from now. Okay. So let's figure out the present value of the contract after the delay. Well, now we have that $10 million not as a present value anymore. It's a future value, right? It's something we're going to receive 1 year from now. So I won't write down the equation because hopefully you're starting to absorb it. How are we going to discount that $10 million we're going to receive 1 year from now back to today? Well, we take it, 10 million, right? And we multiply by 1 over 1 plus the interest rate to the power of time. How many years is that 10 million coming in? 1 year. Okay. So hopefully that formula was quick to your brain. So we take the 10 million and multiply by 1 over 1 plus r to the first power, n equals 1 in this case. Okay. So now that 10 million in present value terms, how much is the contract now worth to us today given the delay of a year? 9.524 million, right, approximately. Okay. So how much did that cost our company? That phone call, right, where the owner said, I can't pay you today, I can pay you the 10 million a year from now. How much did that cost our company? Well, we went from having something that had a present value of 10 million, we were going to receive it today, to now something that has a present value of 9.5-ish million. That cost our company $476,190.48. Okay. All right, let's go back to the slides. All right, it's important when we're moving money through time, we're going from a future value to a present value or vice versa, we should use competitive market prices and interest rates. Interest rates are themselves just competitive prices to do this conversion. Then, building towards the NPV decision rule, which we're going to talk about in a moment, once we quantify all the costs and benefits of a decision, we can apply the valuation principle to determine whether the decision adds value to the firm. So typically what we do is we take the present value of all the costs and benefits. So we have the present value of all the benefits, the present value of all the costs, and we compare them. So we get them in common terms, and the common terms are typically present terms, today's terms. Okay, so the NPV decision rule is a direct application of the valuation principle. So here it is. If the present value of all the benefits exceeds the present value of all the costs, then according to the NPV decision rule, this decision adds value to the firm. So this rule is called the NPV decision rule because we're simply calculating the present value of the benefits net the present value of the costs, hence the NPV decision rule. So what's the logic behind the NPV decision rule? Well, a common financial decision that managers have to make is whether to accept or reject a project. Think about the NPV of rejecting a project. If we don't take the project, we don't incur any benefits, we don't incur any costs. By definition, rejecting the project has an NPV equal to 0, right? Because there are no new costs and no new benefits. Okay? So the NPV decision rule says the following. We should accept positive NPV projects. Positive NPV projects, remember, add value to the firm today. It's just like receiving the NPV amount in cash today. We want to do that. Okay? We should reject negative NPV projects. Why? Well, negative NPV projects would subtract, minus value to the firm if we took them. But we don't have to take them, right? We can pass on them, and therefore, rather than having a negative NPV, we could have a zero NPV, right? So that's why we should reject negative NPV projects. Now, there will be some cases in which we'll have projects which are mutually exclusive. Imagine we're a firm and we're thinking about what to do with a spare warehouse. We could do project A in the warehouse or project B in the warehouse. But importantly, if we do project A, we can't do project B. They're so-called mutually exclusive. Doing one excludes the other. In the case of mutually exclusive projects, choose the one that has the highest NPV, adds the most value to the firm. Hopefully that's intuitive. Okay, let's do a couple of examples. After saving $2,000 driving Uber, you're about to buy a UHD 8K TV. You notice that the store is offering 1 year same as cash deal. So you can take the TV home today and pay nothing until 1 year from now, when you will owe the store the $2,000 purchase price. If your savings account earns 5% per year, what is the NPV of this offer? And then show that its NPV represents cash in your pocket. All right, so let's jump to the Excel sheet. We're on the slide 13 tab, and you'll see I have the problem information here already. So the TV price, remember, is $2,000. We get to delay paying that price for 1 year, okay? And the interest rate at the bank is 5%. So think about the following. Think about, you have the $2,000 today, but you don't have to pay the $2,000 today for the TV. You can put away some fraction of that $2,000 in the bank so that it grows to be the $2,000 you need for the TV in 1 year. So the first objective is, can we figure out how much we need to put in the bank today so that it will grow to be $2,000 1 year from now? Take it out of the bank, pay for the TV, okay? So think about our equation, our fundamental equation, which relates future values and present values. I have a future value of $2,000 in 1 year, and the interest rate is 5%. So the present value, the money I need today so that I can make the $2,000 payment in 1 year with an interest rate of 5%, is going to be what? Well, PV is going to be FV, this $2,000, right, divided by 1 plus the interest rate to the power 1. All right. Remember the formula. PV equals FV times 1 over 1 plus R to the n. That's the same thing as just the FV divided by 1 plus R to the n, and which is what I've done here. I get $1,904.76. So think about it. You get to pick up a $2,000 TV today. It's worth $2,000. But today, you only need to pay $1,904.76 for it. So the NPV is just the difference today, difference between the two. I have a $2,000 TV coming to me today. I only am paying $1,904.76 for it, right? So the difference is $95.24. This acts like cash in my pocket today. Think about it. I would have had to pay the $2,000 out for the TV today if it wasn't for this great deal, Right? Now I get to delay a year and save $95.24. That's money in my pocket today that I would not have had but for the deal. So the NPV, $95.24. Again, I'm getting something whose value benefit is $2,000. I'm getting a $2,000 TV, and I'm effectively paying $1904.76 for it. That gives me an NPV, right? The present value of the benefit, that's the $2,000 TV, minus the cost, that's $1904.76 of $95.24. All right, let's jump back to our slides for the second problem. Your two neighborhood banks are offering specials. One is offering a special rate on deposits of 5%, and the other is offering a special rate on loans of 4%. Show that this represents a positive NPV opportunity. So in one bank, I can deposit money and it will grow at 5% per year. And in another bank, I can take out a loan and I will owe 4% per year, a loan whose interest rate is 4% per year. Okay. So already, hopefully your wheels are turning, thinking about how I can create a positive NPV opportunity off of these differential rates. All right, let's jump back to Excel. And again, I have here the terms in the problem. The deposit rate is 5%. The loan rate is 4%. So we want to show that this is a positive NPV opportunity. Okay. Well, let's start with the following. Suppose we borrowed $1,000 today. Take a moment and think about what we want to do. Let's start with $1,000. Does everyone agree we want to borrow $1,000 at 4% and go take that money and deposit it and get 5%? We want to borrow at the smaller rate and invest at the larger rate. Okay? So think about it. I borrow $1,000 at 4%. Okay? And I deposit that money at the bank that's offering a deposit rate of 5%. So let's first ask ourselves, if I deposit the money, the $1,000 at 5%, how much will be in my account in 1 year? Well, I know how to calculate that. I start with my present value of $1,000 and I grow it at 1 plus the interest rate. It's growing at an interest rate of 5%. That's the deposit rate. So do you agree that there will be $1,050 sitting in the account in 1 year? Okay. Well, because I borrowed the $1,000 at a 4% loan rate, how much do I need to pay back to the bank I borrowed from? Well, they're going to want the principal, the $1,000, right, plus the interest, 4% of $1,000. We know that's $40. They're going to want $1,040 back. How would I figure that out? $1,000 times 1 plus the loan rate. So think about it. Sitting in my account that I deposited the money from is $1,050. I need to pay off the bank I borrowed the $1,000 from $1,040. So out of the account that I have $1,050 in, I take $1,040 out of it and go pay off the bank that I borrowed the $1,000 from. Does it make sense to you then sitting left over in my account in 1 year is $10? So this transaction, all the gymnastics necessary to execute this transaction means I have $10 sitting in an account in 1 year. Okay? Right. Well, what is then the net present value of that transaction? Well, I have $10 sitting in the account 1 year from now. Right? It didn't cost me any of my money today. Right? I borrowed from Bank 1 at 4%, deposited it at bank 2 at 5%, none of my own money. So I have this free $10 sitting 1 year from now. Well, that's not a net present value, right? It's sitting there 1 year from now, the $10. So in order to get the NPV, I need to discount that $10 back to today. Or said another way, how much could I have invested in the deposit account today so that it would grow to be $10 a year from now? Again, we know how to do that. We take the FV, the future value, and divide by 1 plus that rate, which is 5%, to the first power. $9.52 is the NPV. Okay? This transaction is like having $9.52 cash in my pocket today. All right, let's jump back to our slides. So that last example is what we call an arbitrage. Okay. More generally, an arbitrage is the process of trading to take advantage of equivalent goods that have different prices in different competitive markets, right? In our example, right, the loan rate was different than the deposit rate, and we could take advantage of those differential prices, right, for borrowing and investing. Okay. The possibility of arbitrage keeps price differences from occurring, or at least lasting a long time. Let's think about the previous example. If people notice this arbitrage, what do you think would happen? Well, lots of people are going to want to borrow at the bank that's loaning out at 4%. So there's going to be a demand for borrowing at 4%, 4%, 4%. Because there's such a demand for borrowing at 4%, what do you think that bank would do? Well, it might start increasing its loan rate, maybe 4.25, maybe 4.35, maybe 4.5%. Likewise, there's going to be strong demand to deposit at 5%, right? And so because of all this demand to deposit at 5%, that bank might think, we don't have to give people then 5%. We can give 4.9% or 4.8%. And those arbitrage forces are going to do what? Push that 4% rate up, that 5% rate down, and the arbitrage is going to close. Right? This is an enforcement of the law of one price, right? Those prices, again, interest rates are just prices, should be the same, right? Okay, so those arbitrage forces are what helps enforce the law of one price. That goods that are equivalent or securities that trade simultaneously in different competitive markets should trade at the same price. Okay. All right, let's do one more NPV example, and then we'll summarize. Your firm has the opportunity to make a $20,000 investment that will return $22,000 for sure in 1 year. Alternatively, you can borrow or lend at the bank at 6% interest. What is the NPV of the investment, and what should you do? And then as a follow-up question, what should you do if you don't have the money for the investment? All right, let's jump to our Excel spreadsheet. We are on slide 15. So you can see I've written down the key inputs to the problem. The project has an initial cost of $20,000, a cash flow in 1 year of $22,000. The interest rate is 6%, and we're being asked what the NPV is. So remember, the NPV is the present value of all the benefits minus the present value of all the costs. Well, the cost part is simple. And we know its present value. The amount that we need to pay out today, the initial cost, is $20,000. So that part is all set. The part we have to make a calculation for is to get the present value of the benefit. Right? What is the benefit? The benefit is the $22,000, which is coming to us in 1 year. So let's do that. So let's calculate the present value of $22,000 coming to us 1 year from now if the interest rate or discount rate is 6%. So we would put $22,000 and divide by 1 plus the interest rate, right? To the power of 1, we're going to discount back 1 period, right? Because it's coming to us in 1 year. So now we've taken the present value of the benefit, and now we need to subtract off the initial cost, right? This is the present value of the cost, the time zero value of the cost, $20,000. So the NPV in this example is $754.72 positive. So it's positive NPV. Remember, the question asks us, what is our financial decision? What would we do? Well, according to the NPV decision rule, if this is positive NPV, then we would accept the project or take the project. Okay? Now, had we done this calculation and come up with a negative value, remind yourself what the NPV decision rule says to do. It says to reject the project. So because this is positive, we accept the project. Okay, and then remember, the second part of the problem said, well, what if we didn't have that $20,000 today? Remember, that's how much our initial cost is today. We need to pay that out today. What if we didn't have the $20,000 today? Well, how would the problem change? Well, I want to show you the NPV wouldn't change at all. Okay, so let's think about it. Well, if we didn't have the $20,000 today, what would we do? Well, remember, the problem told us that we could borrow or lend at that 6% interest rate. So what we do is we would borrow that $20,000 from the bank. Now, we borrow it at 6%, which means in 1 year, let's calculate how much we are going to owe the bank. Well, we borrowed the $20,000. I'm going to go up and just grab this $20,000. That's how much we borrowed from the bank, right? And it's going to grow 1 period at 6%. Okay? So hopefully everyone's comfortable with the fact that in 1 year, we will owe the bank $21,200. Okay? But we'll have more than that from the project. Remember, we borrowed the $20,000, invested it in the project. The project is going to bring to us $22,000 in 1 year. So after 1 year, we're going to have the $22,000 from the project. We're going to need to pay off the $21,200. That's how much we owe the bank. So in 1 year, we'll have $800 net, right? Positive. Again, we'll get $22,000 from the project. We owe the bank $21,200. That's a difference of $800. Now, that is not the net present value, right? Because this isn't a PV. This is an FV, right? This is an amount that we will have in 1 year. So to figure out how much this is worth at time zero, ask yourself, what do we need to do? And hopefully the answer is discount it back 1 year, right? Because this is a future value. This is sitting 1 year from now. So we need to figure out its present value. So we're going to take this $800 and discount it back to today. So we're going to say equals our $800, and we're going to divide it by 1 plus the discount rate of 6%. Close parentheses. Obviously, it's to the power of 1, so I don't even need to write that there, right? I'm discounting it back 1 period. And so I get $754.72. That's exactly the same number I got before. So what did we just show? It's irrelevant whether we have the $20,000 cost today or not. We could finance it. We could borrow it. If we have it, we could just use it. We get the same net present value. Good. Let's go back to our slides. So just to sum up, a good financial decision is when the value of the benefits exceeds the value of the costs. Such a decision is good because it increases the value of the firm. How much does it increase the value of the firm by? The amount of the NPV that we calculate. The NPV decision rule is a direct application of the valuation principle and is how most firms make financial decisions in practice. All right, last thing for this topic. Recall the formula which relates future values and present values. We can see it here. Right. Remember this formula that we've used throughout this topic? Well, we know this formula has 4 components. It has the FV, it has the PV, it has the R, and it has the N. Okay. So far in our discussion, we have introduced the formulas labeled 1 and 2 here. We've shown FV on the left-hand side and PV on the left-hand side. Okay? So we've gotten FV alone and PV alone. But of course, because there are 4 variables in this formula, in principle, we can solve for any of those 4. So what I'm showing you in formulas number 3 and 4 is the formula for solving for R, the interest rate, or N, the number of periods, number of years. Okay? So what if we want to know the rate of return or the number of years? Well, these are the formulas below for those. Okay? So R equals FV over PV to the 1 over N minus 1. Again, just trust that I've done the algebra correctly for this. And in the case for solving for N, N equals ln FV over PV, all divided by ln 1 plus R. Okay. Now, important to note, this is our single cash flow formula. In another topic, we're going to discuss multiple cash flows. But this is the correct formula for a single cash flow. Okay, for discounting or growing a single cash flow according to R and N. All right, with that in mind, let's finish with a couple of problems that solve for R and N so you can get your feet wet with understanding how to solve for these problems as well. You'll need to know how to solve for any of the components of the single cash flow formula. All right, first problem. You have $1,000. You want it to grow to $1,790.85 in 10 years. You're very particular. That's a very specific number. What rate of return, compounded annually, do you need? Well, think about it. The question is asking what rate of return do you need? So it is asking for the R in the formula, correct? The R. So remind yourself what the formula for R looks like. Again, from the previous slide, R equals FV over PV to the 1 over N minus 1. So in order to solve this problem, we're going to use this formula. So let's jump to our Excel sheet and do it. Let me write out the formula just so we can keep it in mind. R equals FV over PV all to the 1 over N minus 1. All right, so let's do it. So R is going to be the following. FV over PV all to the 1 over N minus 1. and we get 6%. So the answer is 6%. So what interest rate has you start at $1,000, grow at that rate for 10 years, and finish at $1,790.85? The answer is an interest rate of 6%. All right, let's erase this and jump back to our slides and tackle our final question. How many years will it take an initial investment of $300 to grow to $774 if it's invested at 9% compounded annually? Well, the question is how many years? So in the single cash flow formula, this problem is asking for the N. And what do we know? We know the FV, that future value, is 774. We know the PV is 300. And we know the R is 9%. Remind yourself what the formula for N looks like. It's 2 slides up. It's down here. N equals the natural log of FV over PV, all divided by the natural log of 1 plus R. So again, let's jump to Excel and execute this. On the final slide tab, let me write the formula. N equals the natural log of FV over PV, all over the natural log of 1 plus R. Okay, so this is the formula that we're going to execute. Let's do it. So we're going to say equals ln FV over PV, all divided by ln 1 plus R. And so the answer to the question of if you start with a PV of 300, finish with an FV of 774, and the interest rate all along was 9%, how many years was it? The answer is 11 years. All right, back to the slides. All right, and that's it. So hopefully in this topic, you're starting to get comfortable with this intuition of time value of money. Hopefully you're starting to absorb this key equation for single cash flows, which relates future values and present values, and you get comfortable with solving for any one of the 4 components in this formula.